So today we're going to cover Chapter 3, Lesson 4. Today we're going to be doing proofs with perpendicular lines. So the first thing we're going to talk about, though, is the distance from a point to a line. And the distance, whenever they're asking you to calculate it from a point to a line, is always going to be the length of the perpendicular segment from the point to the line. This perpendicular segment is always going to be the shortest distance between a point and the line. So for example, in the diagram here, to get from point A up here down to line K, the distance they're going to want us to calculate is how long this segment AB is. Technically, I could put another point here and call it C, and I could draw another segment here from A to C, but this would not be the shortest distance. So when they're asking you to find the distance from a point to a line, you're always going to calculate the distance for the perpendicular segment. So if this maybe little story helps you to remember, let's say I have a river. These are the banks of my river, and here's the water. And I want to swim across this river. But this river is infested with alligators. And I want to get across this river the fastest way. So when I go to swim across the river, I am going to swim the perpendicular distance to get to the other side of the river. So if I ask you to find point A to line K, it's going to be this perpendicular segment of AB. I would not want to swim from way over there to this point over here, or even to this point. And on the test, they're going to give you a picture with a bunch of lines drawn in. And you're going to have to figure out which one is the correct distance, and it's going to be the one with the right angle. It's going to be the perpendicular segment. And we're going to see that on the next slide. Okay, so example 1, it wants us to find the distance from point A to line BD. Now, remember, when they ask you to find a distance from a point to a line, they're asking us to find the length of the perpendicular segment. So I'm going to be finding the length of segment AC. I don't want you to do AD or AB because those are not perpendicular. So I need to remember my distance formula from the beginning back in August. And the distance formula that, again, you need to memorize for the test and for the homework tonight. The distance formula is, again, you're going to be using two order pairs. So x2 or sub 2 minus x sub 1 squared. And then subtract the y, so y sub 2 minus y sub 1 squared, and it's all under a square root symbol. This is going to give you the distance of a segment. So in this particular picture, the distance I want to calculate is going to be the length of AC, because that is the one that is perpendicular from point A to line BD. So A's order pair is the order pair -3, +3, and C's order pair is +1, -1. I'm going to go ahead and label my order pairs just to make it easier for me. This will be my x sub 1 and my y, so this is my order pair number 1, and then C will be my order pair number 2. So now I can plug those four numbers into the distance formula. So I'm going to plug in 1 minus -3 squared plus -1 minus 3 squared. And it's all under the square root symbol. And this is going to give me the length of AC. So I'm going to go ahead and simplify what's in the parentheses. This becomes 1 plus 3 squared. Over here, this just becomes -4 squared. 1 plus 3 is 4. Okay, and then here, I'll just rewrite the -4 again. So now I need to square both of those and then add them. So 4 squared is 16. Negative 4 squared is also 16. I'm now going to add them, and I get 32. Now, this is where we need to leave it in simplest radical form. Now, on big ideas, you're going to square root this, and in big ideas, you're going to enter, this is going to give you 5.65 something, so round it to the tens place. Big ideas, you're going to enter this as 5.7. However, in your work, you're going to keep going, and you're going to break down the square root of 32. So you're going to do a factor tree. So you could either, if you recognize that 2 times 16 is 32, and then the square root of 16 is 4. So the simplest radical form is going to be 4 square root 2. This is what I'm going to be looking for in your work, and this is how you're going to answer it on the test next Tuesday. Now, let's say you didn't want to do 16 times 2. Let's say instead you thought, you know what, I'm going to do 4 times 8. It doesn't matter what you start with. And again, if you don't like breaking it down midway, keep going till it's prime. That way works as well. So 4 becomes 2 and 2. 8 becomes 4 and 2. I'm still not at prime, so let me just keep bringing everything down. Now I have all prime numbers. Now I go back and look for my pairs. So I have a pair of 2's here, so a 2 comes out. A pair of 2's here, a 2 comes out. And then this 2 that's here, he doesn't have a pair, so he stays underneath. And then you're going to multiply the 2 pairs that came out. So these 2 get multiplied together, and you get the same answer you got when you did 16 times 2. It doesn't matter what you start multiplying with, as long as you keep breaking it down till it's prime, and then look for the perfect squares or the pairs. Next, we're going to talk about a perpendicular bisector. And in this particular picture, the perpendicular bisector of line segment PQ is going to be line N with the following 2 properties. N must be perpendicular to segment PQ, and N must also pass through the midpoint, which is point M, of PQ. Remember, a bisector creates 2 congruent pieces. So we already talked about segment bisectors, but we didn't specify that they had to be perpendicular. So what we're going to be looking for when it's a perpendicular bisector is that it's got the little right angle. In addition, we would look for the 2 congruency marks, indicating that PQ here was split into 2 congruent pieces, and that's how I can tell it was bisected. So we're looking for the right angle and the congruency marks to indicate that it's a perpendicular bisector. Now, we could have had just a plain old bisector. Let's say I had PQ here. And we could have even M here. And I could have a line that comes through here. Without the right angle, the only thing that I can tell here is that this, and I could call this line L, all I can say here is line L is a bisector. Because it doesn't have the right angle, it's not a perpendicular bisector. So no matter if it's a regular bisector or perpendicular, it's still splitting that segment into 2 congruent pieces. What makes line L, what would have made it a perpendicular bisector, is the right angle. So the first theorem that we're going to use to prove things about perpendicular lines is called the linear pair perpendicular theorem. So here it states that if 2 lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So if you think about it, if you have a straight line or a linear pair of angles, know that they're going to both equal 180. So if you were to divide 180 by 2, and since both angles are congruent, both angles would be 90 degrees. So as soon as you're given a linear pair, and if they have congruency marks, you can also tell that these are right angles, and you can conclude that line G is perpendicular to line H, just by being given that 1 and 2 are congruent. You wouldn't have needed to show that they're right angles. As soon as you see they're congruent, you're going to be able to put into your proof that they are right angles, which would make them perpendicular. And again, we could do the same thing that I showed you before. If you have line H, and then if we were to not draw a perpendicular one, if they had like marks like this, then we would say that, and then if you had congruency marks here, well, we couldn't tell that this is perpendicular because they're two different numbers. So like, let's say this is 110 and this is 70. We could not tell that G is perpendicular to H because there is no right angle marking here. These are a linear pair, but they're not congruent angles. The next two theorems sound very similar, but they give you a different result. The next theorem is called the perpendicular transversal theorem. And this one states that in a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So notice in the picture, the little red arrows indicating that H and K are parallel. And then if one of the lines that's parallel is perpendicular to line J, which is that transversal, then I could also say that J is also perpendicular to K. And if you think about it, once you're given that you have parallel lines, we can also show that we have corresponding angles. And corresponding angles are congruent. So right there, we could put in our right angle, which then tells us that J is perpendicular to K. We could have also drawn alternate exterior. I could have put the right angle over here. Either way, as soon as you put in one right angle out of those four, it's going to make J and K perpendicular. The next theorem is called the lines perpendicular to a transversal theorem. And in a plane, if two lines are perpendicular to the same line, then they're parallel to each other. So remember in the other slide, the lines were given to us as parallel and one line was perpendicular. Now we're starting out with both lines being perpendicular, and then we can prove that the other two lines are parallel. So again, if you look at it, we could use our corresponding angles converse. Another way to do this, because we have a pair of corresponding angles here that are marked as both being right angles, and we also learned our all right angles are congruent, then we could state by the corresponding angles converse that M and N are parallel. But we don't need to do that. Now we have a new theorem called the lines perpendicular to a transversal theorem. All we would be looking for is that both lines are perpendicular to the same line. All right, last slide, application. It says the photo shows the layout of a neighborhood. Determine which lines, if any, must be parallel in the diagram. Explain your reasoning. Now, I'm going to go ahead and zoom in here because it's kind of hard to see. So I'm going to go ahead and rewrite the names of these lines. So if you notice, line S is right here. So there's a little S here. Let me do it. So this is an S right here. And then this one's T. This one's U. This one's P. And this one's Q. And then also one other thing I want to bring to your attention is the fact that you have some right angles in here. So I've got a right angle right here and right here. And then I've got another one right here. So this is what I'm going to use to come up with the parallel lines. And the last theorem we just covered, the lines perpendicular to a transversal theorem, that's what I'm going to be using. So if you notice in this picture, both lines P and Q here, so this is P, this is Q, both lines P and Q are both perpendicular, right here, the right angle, to line S. So I could state, since they're perpendicular, since they're both perpendicular to S, I can say that P is parallel to Q by the lines perpendicular to a transversal theorem. So let me go ahead and write that out. So lines P and Q are both perpendicular to line S. So by the lines perpendicular to a transversal theorem, I'm going to abbreviate theorem as THM, I can say that P is parallel to Q. Now, I also have lines S and T here that are also perpendicular to line Q. So I have another pair of parallels. I can say S and T are parallel because they're both perpendicular to Q using the same theorem. So I can also state that lines S and T are both perpendicular to line Q. So by this same theorem, so by the lines, I should have lines perpendicular to a transversal theorem, I can state that S is parallel to T. So the two pairs, again, are going to be P parallel to Q and S parallel to T. Because they're both perpendicular to the same line, I can state that they are parallel. Okay, so remember, you're accessing big ideas through Canvas. Remember, it's on that menu along the side. You scroll to the bottom, you find the words big ideas, you click there, and it takes you right into the Big Ideas website. So you can go ahead and start your homework. While you're starting your homework, I'm going to be passing back your tests, and we're going to go over the tests.